Alright, so hi everyone. This is the very first video I'm going to be recording for work, so bear with me on this one. I hope it's going to go fairly well. So my name is Thibaut, and today's video is going to be about snapclust, which is a method that we've been publishing recently with a bunch of colleagues in methods in ecology and evolution. And this is the article that we'll be discussing. So snapclust essentially is a method for genetic clustering. So I went into the details, the technical details of how the method works. I will tell you a little bit about what it does. For details, you can go back to the paper, and I will focus most of it in like demonstrating how it works in practice. So what does it do? Well, basically, most people that have been analyzing genetic data will have used some kind of clustering methods. So this one in that respect is not very different from, say, what structure does. In fact, it's very similar to what structure tries to do, which is essentially have a highly Weinberg model to put a likelihood on a given genotype given allele frequencies in a cluster. So if I tell you this is a population with a distribution of allele frequencies, which is this and that, what are the probabilities that a genotype was generated under this population versus another population? And basically these probabilities are going to be used to define group membership probabilities. So structure, for instance, will try to do that in a Bayesian framework, where you'll get a posterior distribution of group membership probabilities and so on and so forth. And it's typically fairly computer intensive. So it's been very popular, and I think I haven't seen one person not complain about how long it was to run structure on a decently sized data set. But what it tries to do essentially is a fairly sensible thing. By far and large, snapclust tries to do pretty much the same thing, only faster. And by no means is it the revolution in that respect. Many other methods have tried to do that. I guess the reason why we developed that was that there was a fairly neat trick to kind of boost computations and make and just get results really fast. And the other point was to make this available in R, where there's already a lot of tools for genetic data analysis. So that one was kind of missing, and it was good to, at least I was interested in having it in R. And so what's the trick? Well, basically the trick is that rather than treat that as a Bayesian method, a Bayesian problem, we treat that as a likelihood optimization problem. On the assumption that very often people don't really use the statistical uncertainty associated to group membership probabilities that you can get from a Bayesian method. Bayesian methods are great. I'm involved in the development of a bunch of them, but in this case, I thought we can treat that as an optimization problem more than a Bayesian problem. And the second trick here is that this is a very complex problem, basically. That means the parameter space is fairly large. There's many different combinations that you can explore to try and find optimal clusters. And rather than start from a completely random point to proceed to this likelihood optimization, which takes a bit of time because it takes time to compute this likelihood every time you compute it, the trick here is to use some like quick and dirty approach to initialize the algorithm. So quick and dirty, not that dirty, but fairly quick, in the sense of a geometric approach. So some kind of clustering method that doesn't use a likelihood computation, that only relies on distances and is known to be computer efficient. So there's a few implementations you can think of. There's different brands of hierarchical clustering. I think by default we are using word clustering or k-means clustering, which is not a hierarchical clustering. So you've got two options there, but both of them are drastically faster, like thousands of times faster than typical likelihood optimization. And once we use this to get to a point where we have already a decent clustering solution, it's just small tweaks that we need to do to actually have a maximum likelihood solution. The other thing we do with this method is actually be able to tease apart hybrids. So whenever you have hybrids between two parental classes, and these parental populations have been sampled. You can try to identify hybrids between these two, whether they're like F1 generations or different variants of backcrosses between one parental population and a hybrid population. All right, so that was an outline of the method, and again, go back to the paper if you're interested. What I want to illustrate now is how you can actually use the method. So it's all implemented in R, so we're going to start by closing this browser, and I've been opening here RStudio project. Disclaimer, I don't use RStudio, I don't even use Windows most of the time. I'm only using it here for the purpose of this video. I use Linux and Emacs most of the time, so this is gonna be, you know, things may go wrong. Well, let's see how it goes. So I've got a bit of an empty script here. I've opened, this is my R script here, this is my console. You should be more familiar than me. I'm sure most of you are using RStudio, so you must know how this is basically all set up. Right, so this is a URL to the paper. I will share this script online. I'll put it in the description of the video so you can access it later. So this way you'll be able to find a way to the paper if you're interested. The first thing you want to do is make sure you've got the latest version of adegenet installed, because that's where snapclust is implemented. And I've just released one 3 days ago, so this is really recent things. So if you want to install the latest version, you basically want to use install packages and adegenet between quotes. Okay, control return, I think should evaluate this line. Yes, amazing. Right. So here you can see that it's downloading the zip, and down it's installed. It's very fast on Windows because you just download a file and then zip it. You don't need to recompile everything as you do on Linux. So okay, so now the latest version of adegenet's been installed, and I just need to load the package. So library of adegenet is what you want to use. Okay, there we go. And if we're lucky, we'll have a small message, there we go, telling us which version has been installed. So this one should read 2.1.1. If you are watching this video later, this message may be different. You may get especially a different version number. It should be at least 2.1.1. And it's quite important you use this version as opposed to an outdated GitHub version, which was the development version of adegenet, because we fixed some bugs in this like official release. So make sure you're using the latest version, either the CRAN version or the current Devil version. Right. So now that we have adegenet, what do we do to know more about snapclust? Well, the first thing is going to be, it's always the same thing, just check the doc. So the first thing I'm going to do is check what documentation I have on snapclust. I'm going to use apropos, which I think is French actually, talking about a given topic, apropos, adegenet, and that is wrong. That's not what I wanted to check. I wanted to check snapclust. Okay, so bear with me on this one. Right, that is better. So basically what apropos does is like look for a keyword in different manual pages that you can check. And so basically this tells you that there's a bunch of topics that relate to snapclust. So in these you have different pages there. All the AIC, BIC, KIC are just summary statistics that we'll use later to identify optimal numbers of clusters, so we won't get into that for now. The main thing we want to check are these ones, snapclust and snapclust choosekay. The first one is going to be to find clustering solutions, so that's going to be the main function. This one is snapclust choosekay, is the one we will be using when we don't know what the optimal number of cluster is and we try to find out. So I'm going to check the first one first, and I'm going to add this here to the script. So snapclust, question mark snapclust, right? Let's evaluate this and let's have a look at the documentation. Okay, so there's a bit of blah blah telling you what the method is. There's also some details further down, so I encourage you to check it out, especially if you want to know more about the different modes you can use. There's one for the basic clustering and one to look for hybrids. So I won't look at the doc with you too much because you can read it. You should read it at very least before asking questions. But what we can do is go through some examples together. So the first thing that we're doing here is just load a very simple example with a dataset called microbove. Microbove stands for microsatellites because it's microsatellites data, and bove for bovine. So this is basically the FAO panel for biodiversity assessment based on microsats. I don't know if it's still the same panel now, but at least it was when this dataset was published nearly 8-9 years ago. Okay, so I'm gonna run this, and I just loaded the dataset. So if I say microbove of this and return, it will display. I'm gonna move this up a little bit. Okay, so this is a genet object. So this is the typical class of object that you'll be using in adegenet to store genetic data, whether these are SNPs or amino acid variation or microsat or AFLP, whatever markers you have. It's going to be a genet object. And snapclust is only so far implemented for genet object. If you want to know more about how you can get these dataset into R, if you've got an external data file, not a preloaded dataset as this one, just check the basics tutorial. It's all documented in there. There's a bunch of formats that you can actually use there. And then you can see the example here running first find clusters and then using snapclust on this dataset. And I'm going to tweak that actually. I'm not going to use find clusters as a prior step. I'm going to go straight away for snapclust. So I'm going to even type this. So res equals snapclust of microbove, and I think I don't even need, no, I will need to say how many clusters I want. I'm going to say 15 in this case because I know there's 15 breeds in this data set, which contain about 700 individuals. Okay, so let's have a look. Okay, so the data set, the number of clusters, that's all I should know, I should have to know. Let's see how it goes. All right, so it's doing something. It's not a huge data set, but it's decent. You know, there's like almost 400 alleles, 30 microsats, 700 individuals, and right, it's done. So it's all there. If I type res and return, oh, okay, I've got a lot of things in there. So I may not want to have a look at like all of that, at least not visually. I will plot these results in a minute. But basically there's a few indicators and it's all documented again, so you can go back to that. What does it tell you here? Well, we'll tell you one important thing is whether the algorithm converged or not. So in this case, yes, it did converge, which is a good sign. If it hasn't, I mean, there's been a problem. You need to run it for longer. And it's converged very, very fast in 9 iterations, and iter is the number of iterations. Right, so it means that in this fast, quick and dirty pre-optimization procedure we've done using word clustering, we got fairly close to the maximum likelihood solution, because with only 9 iterations we could end up with a maximum likelihood solution, which, you know, if you wanted to compare that with structure, that would be the length of your MCMC, including the burn-in. So, you know, we're talking probably hundreds of thousands of iteration for that kind of data set. And again, it's not directly comparable because you're comparing a maximum likelihood solution to an MCMC, which can run forever, but still we haven't had to wait a long time to get the results. So let's have a look at these. Like, there's group membership probabilities, which are the numbers you can see here, which is what I want to visualize here. So the function you want to use for this is the compo plot. It's stands for composition plot, and it's been implemented for a bunch of different things, including different objects, including snapclust results. So if we have a look at this, there we go. Here I think I may even be able to open this in a full page. I don't know. Oh, this is why I hate RStudio. Anyway, so what you get here are group membership probabilities. So this is really very much like a structure plot. So every bar is a different individual. You've got 704 individuals in there, and they're colored by their different clusters. And what you can see here is that some clusters are very, very well defined and others look a little bit more mixed, like these individuals here. And you could use these kind of clustering to visualize your data further. You could use a DAPC to try and visualize this data. I may illustrate that in a different video at a further stage, but for now I'm just going to focus on snapclust, purely snapclust. Right, so in a nutshell, that's how you can use snapclust on your own data. I'm going to illustrate two more things now. One thing is what happens when you simulate hybrids and how you can try to identify hybrids, and the last one will be how to choose the optimal number of clusters. Right, so the first thing is I'm going to be further down in this example. What I'm doing here is simulate hybrids. And this is something you'll find in the tutorial that I link to further down the line. But basically, in practice, you won't have to simulate hybrids, right? I just need to simulate hybrids here to illustrate how the method works with hybrids. So how do you do that? Well, there's a fairly simple way to do this in adegenet. Basically, the process is just this part here. So we're going to go through that together. So the first one is, the first line here says that I'm going to create a new object called zebu, which is subsetting the object microbove. The square bracket operator is for subsetting. Again, if you don't know how to handle, or you want to know more about how to handle GENERATE objects, check the basics tutorial, which detail like many different ways you can use these objects to extract information in a fairly efficient way. So if you say pop equals zebu, zebu is one of the populations in this data set. These will just extract all the individuals from this population here, right? If you wanted to know what the population names were in the dataset, you'd just say pop names of microbove and return, and then it will list all the different populations. And if you want to have the group memberships, just say pop of microbove, and that will tell you what population each individual belongs to, right? That's a factor giving you the group membership for the breed effectively of every individual. Okay, but I digress. So let's go back to my zebus and satyrs. So here I've extracted all the zebus. I'm going to do the same for the satyrs here. Copy paste that. Right. So if I check these objects, they will be GENERATE objects, but this time they contain less individuals, the same number of alleles, but only 50 individuals here, right? So I've extracted the 50 individuals that were from the zebu breed. I've done the same with satyrs. I think it's a fairly balanced data set. Yeah, I've got the same number of satyrs here, which is a different breed, so it's all good. And now I need to simulate hybrids. So how do you simulate hybrids using adegenet? Well, it's fairly simple. What you do is just use this function here, hybridize, and provide the two parental populations and say n, the number of individuals you want to simulate, the number of hybrids you want. So here I want 30 hybrids. Done. Okay, I've simulated my hybrids there. And if I check this object, I've got 30 individuals, same number of loci as before. And here you'll notice a discrepancy, something that's different. I've got 282 alleles here. If I go back to the previous object, the satyrs had 373 alleles. Now why is that? Well, this happens because by default GENERATE objects only store polymorphism, so polymorphic sites. So what we store effectively is alleles. Now, but just simulating hybrids, just by chance, some alleles have been dropped. Okay, so some alleles that were represented in one or both of the parental populations do not exist in the hybrid population, which is a bit of a problem. Mathematically, that means that these different populations are now embedded in different vector spaces that don't have the same dimensions and not matching dimensions. So it's a bit of a tricky thing. And to cut a long story short, the trick you need to use is this repool, to basically repool all these data together and put them in a comparable space so that they will all have the same alleles. Okay, and X is going to be my new data set that contains the zebu, the satyrs, and the hybrids. So if I press return here, I've got 130 individual, which matches the fact that I've got 50 zebu, 50 satyrs, and 30 hybrids. And now I boil it down to whatever were like common alleles within this data set, which ends up being only 282 alleles. And so I've got this hybrid data set now. And what I'm going to show you is what happens when you run snapclust looking for just two clusters on these data, and this is what this is doing here. And I specify hybrids equals false, which I think is the case by default. So let's run this. Should be reasonably quick. It's right. Okay, so that was very fast. It was very fast because we had a lot less individuals this time. Again, a bit faster than your typical clustering solution. And I'm going to do a compo plot of this using the spectral color palette, and there you go. So what do you see there? You've got the first 50 individuals from the first parental population. That's probably going to be the zebu here because they were first, then the satyrs, and then I've got the hybrids. And this is very odd because you would expect that the hybrids would be 50-50, assigned 50-50, 50% to one parental population, 50% to the other parental population, and that's not what's happening here. And in fact, it's possible to explain why this is the case, but essentially it boils down to the fact that if you imagine that in the geometric space you have one parental population here, the other parental population there, and your hybrid population is sitting right in between. And the fact that it's sitting right in between means that in terms of assignment, individuals will tend to be systematically assigned to whichever population they're closest to. And so it's very, very unlikely that they will effectively be assigned 50-50 to equally to each population. And it's not just like snapclust behaving like this. This will happen with the DAPC as well. If you try to run a DAPC with two clusters in there and you try to assign individuals, even though a principal component analysis will show that the hybrids are right in between the two parental populations, in terms of group assignment probabilities, individuals will be systematically assigned to one or the other parental population, which is annoying because here we're missing the point that they are hybrids. Now, what happens if we start adding hybrids into the mix? So here, I'm just going to rerun the same analysis, except that this time I specify that hybrids equals true, right? And I'm going to copy paste this. Again, it's going to be fairly quick, right? That was almost less than, I would guess, less than a second. I'm going to plot the results of this analysis again. And this is what happens this time. So what you see is the two parental populations well identified, but in this case now you have all the tail here is fully identified as hybrids. This is the yellow color here. And what these terms mean is, like, this is A and B, the two parental populations. This is a hybrid population constructed as equal mixture of the two parental populations. Okay, so 0.5A, 0.5B means 50% of allele frequencies of A and 50% of allele frequencies of B, which exactly means that the allele frequencies of the hybrid population are the average of the two parental populations. And of course, if you've got backcrosses between A and the F1 population, which is there, then you would change these mixture coefficients. I went into the detail of that. This is all documented. If you go back to the help, you'll see that this is effectively documented in here. This is the hybrid coefficient, and you can look at how to specify these. Basically, if you want first or second generation backcross, you'll have to put a 0.25 and a 0.75 in there, or, well, this is all documented. And it's also in the tutorial, so I won't detail that further. So, so that's a quick example of how you can use snapclust to identify genetic clusters, pan-mictic populations, and genetic clusters in the presence of hybrids when you have the two parental populations and hybrids in between. The last point I want to illustrate here is what you do when you don't know what the true K is, and true K being the true number of clusters. And the big disclaimer here is I am not a very strong believer of true K. In fact, I'm pretty much sure that in most cases the true K doesn't exist. And that's a topic for another video maybe. Those of you who've been following courses I've been running on genetic data analysis have heard me rant about this. I'd rather talk about optimal K in the sense that a number of clusters that is a good summary of your data. You know, whether or not your data were actually generated by a pure island model is a very, very different thing. So let's talk about useful summaries here. And I'm gonna go to the doc. I'm gonna open the doc of snapclust choose k, which is the function you can use to choose the number of clusters for snapclust. What it reads on the box. And this function is fairly easy to use as well, at least I hope so. Basically, the main argument is the maximum number of clusters you want to explore. And bear in mind that the more clusters you'll get, you'll try to find, the more computer intensive this is going to be. Because basically what snapclust choose k will do is look for clustering solutions from 1, 2, 3 all the way to the maximum. Okay, so if you put 40, it will go all the way to like 39, 38, 39, 40, which will take a while. So what it will do is explore these different solutions and then get a summary statistic, which is typically a goodness of fit statistic, penalized for the complexity of the model that you're using. In this case, the complexity of the model is going to be entirely dependent on the number of clusters. So how many clusters is it worth adding to the model to have a good summary of my data? And there's different summary statistics that you can use in there. There's an AIC, the AIC corrected for small sample size, the AICC, the Bayesian information criteria, and the KIC, the callback information criteria. So you can try different options and see what works best for your data. But I'm just going to give you a feel for like how it works. So this example here runs a simulated data analysis. So I'm going to first load the simulated data, which was used originally for the DAPC. So these are 600 individuals, 30 loci, and these were simulated from an island model. So I've got 100 individuals from 6 different islands, 6 different populations. And I'm going to show you what happens when you run this analysis using the AIC. So snapclust max equals 10 means I want to explore clustering solutions all the way to 10 clusters, and A is my input data set, and that's all I need. Right, and this is done, so I can plot the results here. It was fairly quick again. And if you look at this, you'll find a typical plot for this kind of output. So what you have on the x-axis is the number of clusters, and you have your summary statistic, your goodness of fit statistic on the y-axis. And AIC is basically a measure of penalized deviance. So the deviance, the lower it is, the better your model fits, basically. So what you can see here is that your AIC decreases as you increase the number of clusters, which is good, and then it kind of stabilizes once it hits k equals 6. And then improvements after that are marginal if they are there at all. And this is typically what you want to look for. You want to, we call that an elbow in the curve, or whatever, sharp decrease indicates that adding clusters is useful. Once you no longer have a sharp decrease, then that means you pretty much hit the optimal number of clusters. And so this is what you get with the AIC. We can check what happens with the KIC. I'm just going to copy paste this. So this is exactly the same, except that this time the information criteria that is used is KIC, and this is how you indicate it. Right, let's run it. It's going to take a couple of seconds to run. And we should be nearly there, and there we go. And I refresh the plot, and the plot here is going to be essentially very, very similar, except that here you see that the KIC increases again, which is even a better sign that the optimal number of clusters is 6. Now bear in mind, this is a simulated data set, so, and this was actually simulated using an island model, so there is a true K in this case, and it's fairly clear cut. On your real data set, on empirical data, very, very often it will not be as clear cut, and you may have a tie between different values of K, in which case, you'll have to think about what is the optimal number of clusters you want to use. Do you want a parsimonious solution, or do you want a more detailed solution where individuals are clustered together into tighter groups? And I think this is everything I wanted to show. I've been running the examples here. The last bit, oh yes, it's good that I've got this. The last bit I need to show you is how to find more about this. There's the paper for the more theoretical aspect. If you want to know more about the practical aspects, you can check the tutorial. There's a tutorial online for snapclust, and to open it up, you can just type adegenet tutorial, And okay, it suggests different options here. You want to use snapclust. And basically what it will do is open a web browser and download this file here, which is a PDF. And there you go. You've got your snapclust tutorial with a bunch of different illustrations, a bit of a blurb about the model and the mathematics behind it. And there's some examples, some of which we have seen together, and some more detailed examples in there, especially with different kinds of hybrids and how you can use backcross and so on and so forth. So that's it for today. Thanks for sticking around. Don't hesitate to post questions in the comments below, and I will put all the links to different resources in the comments as well. So thanks very much, and see you next time.